Gravity surveys. The gravitational field of the Earth is produced by the whole of the Earth. So this mass will be attracted by both this section of the Earth, this section of the Earth, and everywhere else. However, due to Newton's universal law of gravitation, force is equal to minus the gravitational constant times by the product of the two masses over their separation squared, the closer part of the Earth, the one here, exerts the bigger force, as it has the smaller separation. The Earth is not homogeneous, that is, it's not the same everywhere. It has large areas of high density granite, as shown here, lower density limestone, and even lower density oil, close to the surface. Clearly this diagram is not to scale. From force is equal to minus gmm over r squared, the material closer to the surface has a bigger effect on the force than the material further away. This can cause what are called gravitational anomalies, slight changes in the gravitational field. So for instance, if we look at the gravitational field strength as we pass a large area of granite, this would be its normal value, and it would be slightly higher around the granite, returning to its normal value when we pass the granite. The similar thing for oil would show the gravitational field strength reducing slightly due to the lower density oil near the surface. The changes in gravitational field strength are very small but can be detected. To calculate the difference in field strength caused by a deposit of oil with a volume of 50 million cubic meters and a density of 800 kilograms per cubic meter, the centre of mass being 100 meters below the ground, the average soil density of the area is 2000 kilograms per cubic meter. We can calculate the force on 1 kilogram due to the oil using Newton's universal law of gravitation. I'm going to ignore the minus sign from now on, as it's only the magnitude of the force I need. Putting in the values, the gravitational constant, the mass of the oil I've got from the density multiplied by the volume. This is the mass of the 1 kilogram reference mass I'm using, over the separation of 100 meters to the centre of mass squared. This gives a force of 2.67 times 10 to the minus 4 newtons. Now we can calculate the force that would have been produced by the soil, using the same formula, but now with the density of the soil multiplied by the same volume, gives a force of 6.67 times 10 to the minus 4 newtons. So the change in force is the force due to the oil minus the force that would have been caused by the soil, giving a reduction of 4 times 10 to the minus 4 newtons. So we have a change of 4 times 10 to the minus 4 newtons over the average weight of the object of 9.81 newtons, multiplied by 100 gives a change of just 0.004%. Gravimeters can detect tiny changes in gravitational field strength, much smaller than in this example. As distance from the Earth affects field strength, when taking measurements this must also be taken into account. The gravimeters can be mounted on aircraft, and the movement of the aircraft must also be accounted for. Relative gravimeters compare the gravitational field strength with a reference value, whereas absolute gravimeters will measure the actual value of the gravitational field. Relative gravimeters can use the time period of a simple pendulum, or can measure the extension of a spring, rather like a very sensitive spring balance. From the simple pendulum we know that the time period is equal to 2 pi root length over gravitational field strength, so gravitational field strength can be found from 4 pi squared L over t squared. Both of these devices would compare the gravitational field strength with a known region. They are relative gravimeters. Absolute gravimeters will measure the acceleration due to gravity of a freely falling object. In this case, our object is a reflector. It must be in a vacuum to avoid the effects of air resistance. We also have a laser, a partially reflecting mirror, a stationary reflector, and a light detector. Light from the laser will come out towards the mirror. Some will pass straight through to the detector. Some will be reflected and follow this route, reaching the detector by a longer path. The length of this second path varies as the reflector falls towards the mirror. When the two light sources constructively interfere, light will be detected. When they destructively interfere, light will not be detected. The timing of the flashes at the detector allows the acceleration due to gravity to be calculated. They can find changes in g of 1 part in a billion.